Good evening, I'm Narayanan from Horace Mann School, and this is my project in theoretical physics. I worked on this project over the summer of 2021 with my mentors, Dr. Parashar from Johnny Logan College, Dr. Chaudhary from Southern Illinois University, and Dr. Vijay Kumar from Columbia University. The force of static friction, which resists the motion of two contacting surfaces at rest, is something we see everywhere around us. If you've ever tried to push a chair across the living room, you notice that you need to put in a certain amount of force before it actually starts to move. And that's because until that point, you're resisted by the force of static friction. The amount of force that you need to put in to move the chair, which is equal to the maximum value of static friction, is given by this equation from the conventional Coulomb model of static friction. Fs max, the maximum value of static friction, equals μs times Fn, where Fn is the normal force that pushes these two surfaces together, and μs is the coefficient of static friction, a dimensionless empirical quantity that's unique to every pair of materials. Since static friction is so well known, there's been an extensive history of research in understanding it, like the work of Tabor and Hertz, which introduced asperity interlocking and elastic and plastic deformation to the force of static friction, and the work of Deryagin, which incorporated van der Waals interactions to the force of adhesion. But there's still a gap in understanding static friction at a fundamental level. And to approach this question, we want to be very simplistic and consider one interaction only, the van der Waals interaction. Van der Waals forces arise from the dipole-to-dipole interactions between two neutral polarizable atoms. It's these forces that are responsible for holding together the layers of van der Waals materials, which are 3D structures composed of individual 2D layers. Van der Waals materials also have a wide variety of practical applications. They have very low coefficients of static friction between their layers, and it's for that they've been used for decades as solid lubricants. They are also recently emerging for potential use in nanotechnology. Van der Waals materials provide a good test case for understanding the contributions of fundamental forces like the van der Waals force to the force of static friction. That brings us to our research question. What are the contributions of van der Waals and Casimir interactions to the force of static friction? The goal of this project was to better understand how these fundamental interactions contribute to the force of static friction, and in doing so, to derive an analytic expression for the coefficient of static friction, Us. Because it's van der Waals forces that hold together the layers of van der Waals materials, we hypothesized that it was the van der Waals and Casimir interactions that would determine the μs of two-dimensional van der Waals materials. We modeled the layers of van der Waals materials as two infinitely long layers of polarizable plates that extended to infinity in the x and y directions, but had sinusoidal corrugations on their surface only in the y direction. The distance a between the plates represented the interlayer distance of the van der Waals material. The wave number k of the sinusoidal profile represented the periodic structure of atoms within one layer. And the lateral displacement y of one plate represented the shift in the layer stacking. As you can see in the right picture, atoms that are supposed to be in the same planar positions are actually shifted as you go from the bottom layer to the top. We first calculated the interaction energy between these plates using the van der Waals interaction energy in the Casimir polar limit. The van der Waals force is between two neutral and polarizable atoms that have gained dipoles due to quantum fluctuations. We're considering this interaction in the relativistic Casimir polar limit, which takes into account retardation effects from the finite speed of electric field propagation. As you can see, there's now a factor of c, the speed of light, in the numerator, and an extra power of r, the separation distance, in the denominator. There's also an h bar in the numerator that corresponds to the Casimir interaction originating from quantum fluctuations. To calculate the interaction energy between these plates, we use a perturbative expansion in the parameters h1 over a and h2 over a. As you can see, the total interaction energy is the summation, first of the energy between two parallel plates, then the first order terms with one corrugated plate, then the second order terms, out of which one term contains the interaction energy between two corrugated plates. We want to be simplistic, and we use the perturbative expansion in the second order only, meaning that we dropped any terms that were third order or higher. We then calculated the interaction energy per unit area between the plates, and we derived this equation for the interaction energy. Remarkably, we found that there was no interaction energy from the leading order perturbative terms due to the sinusoidal symmetry of a system with one corrugated and one flat plate. What that means is that the simplest perturbative expansion we could have used to calculate the interaction energy per unit area had to be in the next to leading order. Then we derived the equations for the lateral force and normal force per unit area by taking the gradient of the interaction energy. That is, the negative partial derivatives of the interaction energy per unit area with respect to y, the lateral displacement for the lateral force, and a, the vertical displacement for the normal force. Notice that the lateral force varies sinusoidally with respect to the lateral displacement y. And going back to the first expression from the Coulomb model of static friction, Fs max equals mu s times Fn. Our hypothesis is that it is this Casimir lateral force that corresponds to static friction in van der Waals material layers. Rearranging, we say that Fs max equals Fl max, and solving for mu s, we get that mu s equals Fl max over Fn. To get the maximum value of Fl, we take the maximum value of the sine function in the Fl term, which is 1, and we multiply it by the rest of the Fl term, and that gives us Fl max. When we take the ratio of Fl max to Fn, we get an expression for the coefficient of static friction mu s, which is this. Notice first that it only depends on 4 geometric parameters: h1 and h2, the corrugation heights; a, the distance between the layers; and k, the periodicity of the surface corrugations. Notice that while the interaction energy and the lateral normal force contain the sigma, which carried the dielectric dependence of the material, mu s is independent of the polarizability per unit area, and therefore it is independent of the dielectric properties of the material. In addition, while the interaction energy and lateral force are dependent on y, the lateral displacement, mu s is independent of y, which in the case of van der Waals materials means that regardless of how you stack the material, like this, or like this, mu s is independent of any of these stacking configurations. We applied our model to 3 different van der Waals materials: graphene, hexagonal boron nitride, and black phosphorite, and we calculated the coefficient of static friction for these 3 materials. For the hexagonal structures of graphene and hexagonal boron nitride, we used our corrugation path along the short diagonals of this hexagonal structure. In addition, as you can see, when we orient ourselves along this corrugation path, we use the atomic radii as the corrugation. And when we calculated the coefficients of static friction for these 3 materials and compared them to what had previously been reported in the literature, we found a strong agreement between our calculated values and the literature. One thing to note is that our error ranges were determined by using different reported values for the interlayer distance of these materials. Another thing to note is that the study of black phosphorus is an emerging field of research. As such, we were unable to find an exact value for its coefficient of static friction, but we used the mu s of black phosphorus liquid paraffin for completeness in our comparison. This table shows the data for our calculated values of mu s and the reported values, as well as our calculated values for the interaction energy per unit area as compared to literature values for the interaction energy per unit area. I'd like to discuss some potential applications of what we have derived, as well as some limitations of our calculations and future work that could be done to overcome these limitations. This expression for mu s could be used to predict the maximum static friction force in nanotechnology. As I said before, van der Waals materials are gaining increasing interest in this field of nanotechnology due to the 2D nature of their layers. And our expression for mu s could be used anywhere where van der Waals materials are stacked and create interlayer static friction. This would be very useful for an engineer that is designing the nano machine, as it would allow them to predict the maximum static friction force in the nano machine. A concrete example of this is a reconfigurable logic gate, where different layers of van der Waals materials like graphene and hexagonal boron nitride are stacked, which creates interlayer static friction. But that's not all. If we were to incorporate electrostatic effects into our model as well, a similar expression could be derived that calculates mu s in other materials as well. I'd also like to discuss some limitations of our model in our calculation. We used only one-dimensional sinusoidal corrugations, and this was only an approximation, especially for the hexagonal structures of graphene and hexagonal boron nitride. One way to overcome this would be to incorporate corrugations in the Y and the X directions. And as you can see by the right picture, this would better simulate the surfaces of hexagonal structures. In addition, we only considered the zero frequency components of the polarizability because we used the Casimir-Poulter limit. But this could be overcome by going beyond the Casimir-Poulter limit and incorporating frequency-dependent contributions via a full Lifshitz theory approach in future work. We have developed a simplistic model that calculates the coefficient of static friction μs in two-dimensional van der Waals materials entirely from first principles. Our research shows that the coefficient of static friction in van der Waals materials is independent of their stacking configurations or the dielectric properties of the material itself, while it is completely determined by the geometric properties. This expression from US could be used especially in emerging nanotechnology, where it is crucial to reduce the friction between van der Waals materials. And further work could overcome some of our current limitations by improving the treatment of the surface profiles or incorporating other interactions like the electrostatic effects or the frequency-dependent contributions of the van der Waals interaction. And that would allow our model to be extended to other materials as well. That's all for my presentation. Thank you very much for listening.